So here we are in week 7 on Tuesday. We're going to start talking about graph coverage today. Yeah, so graph coverage, we start today. We'll talk about that this week and next week. Next week, assignment 4 is due. Speaking of assignments, I do want to go back and just mention, I did send out an announcement about a potential change to the syllabus that I would like to make to change the way we do participation points, and to also, I'm just going to go ahead and mute somebody there, change the participation points and also change the late scoring for assignments to try to make that a little more, I guess, a little more fair, a little less, you know, if you miss the moment that it was due, you kind of fall off a cliff, right? So if you haven't already taken a look at that, if you haven't already taken a look at the proposed syllabus changes, take a look at that in the discussion group. I'm going to go ahead and put that into effect tomorrow, unless I hear anybody objecting to it. You know, and I want to be very careful about changing the way the grading happens in the middle of the class. Right? This is not what I explained. This is not what you signed up for. So I just want to make sure there's no objections to it. I don't really think there will be, because I think it's really all in your favor. But if you have any concerns about that, please get in touch with me before the end of tomorrow. Okay, and assignment 4, I think I mentioned, that's due next week. By the current rules, due before start of class. By the proposed changes, due by midnight, the end of next Tuesday. Sorry, the end of next Monday. We're back on Mondays next week. I hate Monday classes, but they're better than Friday classes. All right, so let's talk about quizzes here for a minute. Do a quick review of quiz 6. This is posted on Blackboard. Quiz scores. This quiz has pretty much every semester had a little more distribution than many of the quizzes. I think that this is a topic that some people find harder than other folks. So, you know, we're done with input space partitioning for now, and except, of course, for the assignment that you're working on. But the topic will come up again on the final exam. I can assure you there will be a section on the final exam on this. So if you didn't do too well on this week's quiz, I wouldn't worry about it too much. But I would want to be sure that by the end of the semester, you feel like you've got your hands around the topic. The quiz had 2 different and fairly similar questions. I've posted this, so I'm not going to go over it in detail. I would be happy if you have questions about why you were graded the way you were. Please talk to RTA. If you have questions about why the answer is the way it is, then please let me know or post in the discussion group, and we'll talk about it. So I've got a set of answers here for the bounded Q problem. Again, I'm not going to go over these in detail, especially since half of you didn't take this question. And then I've got a bunch of slides for the alternate max problem. All right, so as I said, these are all posted, so you've got a chance to go through them. Again, keep in mind that, you know, there's not always necessarily one correct answer. So these are, you know, obviously I think that these are good answers, but they're not the only possible answers. Okay, so where are we on the House Cup? Still pretty even. So, you know, a little bit up, a little bit of ups and downs, but still fairly even across the board. Everybody is still in it. Yeah, Kyle, I've also found, just as I was getting connected to the class, that Zoom needed to do an update. So, you know, at least I got on early enough for that. Also, my laptop is telling me it wants to do a Windows 11 update, and I told it, no, this is not a good moment. So to recap briefly, I was talking about the proposed changes to the syllabus. Take a look at the take a look at the discussion board for that. And if you have any concerns about that, let me know. If I don't hear any concerns, and I haven't yet, then I'll put that into effect tomorrow night. Assignment 4 is due next week, and we're back to Mondays. And that's about it. This is the end of the quiz 6 review. This is posted so you can go over the questions in detail. And then the last thing, oh, I didn't make it part of this. I did it separately. Let me pull that up. Midterm. So I posted midterm grades today. So let's talk about that a little bit. The way the grade is currently calculated, right? We know that we have in the syllabus how all the grades work out. So what do we have so far that we're basing the midterm grades on? Well, the midterm grades are based 53% on your quiz grades. For that, I've taken your highest 4 out of 6 quiz scores, meaning I dropped the lowest 2. At the end of the semester, I'll be dropping the lowest 3. So I dropped 2 because you can't drop 1.5, even though we're only halfway through. So that maybe is a little bit inflating your quiz score. But typically I have found that the quiz scores in general tends to increase over the semester, right? Kind of increase and stabilize over the semester. So I'm fairly confident or comfortable that dropping your lowest 2 scores at this point gives a reasonable representation. So there have been 6 quizzes. There have been 6 quizzes graded so far. There are 13 quizzes total. So there are, 7 to go.
Professor, one quick question.
Sure.
Yeah, sorry to interrupt.
No problem.
Will quiz 7 still be on Thursday, even though today's course is on Tuesday?
No, I moved quiz 7 to Friday.
Oh, perfect.
So that you've got the same number of days.
Thank you so much.
Sure. Assignments are currently making up 1/3, 33% of your midterm grade. This is made only of assignments 1 and 2. Yes, assignment 3 has turned in, but assignment 3's grading isn't finished yet, so I was not able to incorporate that. I will point out that the assignments, assignment 1 is not worth very much in a scaling perspective, and assignment 2 is only a little bit higher, right? Each of the assignments has a little bit more value or a little bit more weighting as we go. So the assignment portion of the assignment portion of the grade isn't super meaningful right now. Participation is currently 13%. The reason that these are higher than normal is because there's no final exam as part of the midterm grade. And I've graded participation based on a threshold of 5 points so far, meaning if you have my expectation, right, kind of scaled through the course. At the end of the course, 10 participation points is full credit. So right now I said, okay, 5 participation points is full credit as far as the midterm grades go. What do the grades look like? Here they are. I guess I'll let you draw your own conclusions. Typically from here, I usually see more A's than A pluses, and so this is kind of the other way around right now. And I'm perfectly happy with that. The majority of you are doing really good work. So this is presented just so you can see what your grade is. You can see where you kind of fit in on this scale. So how does this grading change to get to the final grading? So all this is in the syllabus, so I'm going to talk about it just very briefly. 40% of your final grade is going to be quizzes. I'm going to take your 10 highest scores, meaning I'm going to drop your lowest 3 out of 13. So if you're feeling like, well, right now I have 3 terrible scores out of my 6, well, if you've got good grades for the rest of the semester, those 3 terrible scores will go away. Assignments will end up being 25% of your final grade. The later assignments have more weight, right? So they count more. Your last assignment counts a lot more than your introduce yourself assignment. Participation is 10%. It'll be based on a final threshold of 10 points. The final exam will be 25%. The final exam, because there is no midterm exam, will contain topics from the entire semester. So that's kind of the overview on midterm grades. That's posted as well in this week's content on Blackboard. And so with that, any questions or discussion on the quiz, the midterm grading, anything else we want to talk about before we jump into the topic for today? Oh, I have one other thing I want to mention. I did do a little bit of adjustment of the groups. We ended up with 2 groups kind of on the small side and 2 groups kind of on the big side and 1 group right in the middle. So I asked for some volunteers from the 2 larger groups. I got, as it turned out, just exactly the number of volunteers that I needed. And so now I've rebalanced the groups and they're all equal sizes, which is nice. So do expect to find a little bit of a different dynamic when we break up into our in-class exercise groups later today. And thank you to those of you who volunteered to change. I appreciate it. So anything else we want to talk about before we move on? All right, let's go ahead and jump into graph coverage then. I guess before I do that, I'll say, input space, input domain modeling, input space coverage, input space partitioning, various names for what we've been doing for the last 2 weeks. That is actually really very, very practical. And that's an approach that I use really all the time. I do a lot of testing at work. I do a lot of consulting about testing at work, and doing input domain modeling is a very common activity. We don't always do it with the same level of rigor, I guess, right? The same level of theoretical rigor that we're doing it in this class. But overall, that's a really common and very, very high value technique. So definitely something you want to keep in your back pocket because it's easily applied to testing and at a lot of different levels, from unit testing all the way up to, high level system testing. So with that, let's dig into graph coverage. So here's kind of our model of the textbook and the class overall. So now we're going to be dealing with graph coverage, which applies to source, design, specs, use cases. We are mostly going to be using graph coverage to deal with source code with a few other little peeks at this or that of other things. So graphs are probably the most commonly used structure for testing, and you can get them from a lot of places. The most common place to get graphs from the perspective of using graphs for testing is to get them from control flow graphs from software. We'll talk a little bit more about control flow graphs. I do have an expectation that you're at least kind of familiar with that, and then that won't come as a big surprise. But we can also get it from other places. We can derive graphs from use cases. We can especially derive graphs from finite state machines or state charts, because frankly, those just are graphs to begin with. When we're doing graph-based testing, we are usually using implementation knowledge, right? Especially if we're doing it for source code. A control flow graph is a slight abstraction of the source code. So this would definitely be, if we want to go back to that white box versus black box terminology, this is very white box, right? We are hands-on with the implementation of the thing that we're testing. So what is a graph? A graph has several attributes, right? A graph has a set of nodes where the set of nodes is not the empty set. So there is at least one node in a graph. And then there's a set of initial nodes where the set of initial nodes is a subset of the full set of nodes, and the set of initial nodes is not the empty set. So we have at least one node in the graph, and we have at least one initial node. And we have a set of final nodes. Again, the set of final nodes is a subset of the total nodes and is not empty. So we have at least one node, we have at least one initial node, we have at least one final node. Then we have a set of edges where each edge connects one node to another node. And these are directed edges. So we have a predecessor node with an edge that leads from there to a successor node. So here are some example graphs. So we have this first graph, we have a set of nodes, 1, 2, 3, 4. We have a set of initial nodes, just that's one. Initial node is usually, I've seen different notation. The textbook and all of my sources are going to use this notation where there's a little arrow that goes into it. And we have a set of final nodes. The set of final nodes is node 4. They are typically, final nodes are typically shown with either a thick border or a double border, and I've kind of chosen to do both here. Then we've got a set of edges, 1 to 2, 1 to 3, 2 to 4, 3 to 4. You can see these arrows. So yes, this passes, this is a graph. This second one is more complex. We have more nodes. We have more initial nodes, 3 of them. We have more final nodes, 3 of them. We have more edges, but still, that has all the characteristics that make it a graph. This fourth one is not a graph because it does not have a set of initial nodes. You might think, oh, well, node 1 is an initial node, but actually there's no input arrow or incoming arrow, initial arrow. I'm not sure what we'd like to call it, but there's nothing there that designates that first node as an initial node. So this is not a legitimate graph.
Is the middle graph missing edge 2, 6?
Is it missing edge 2, 6? It doesn't have edge 2, 6. It has edge 6, 2. If we look at the direction there.
There you go. Yeah.
All right, so it's running from 6 to 2.
Okay.
I have a question so on the second graph. So what is the example that we have for the multiple initial nodes? The first question, and the second question is, since we have multiple initial nodes, so where should we start?
It's a little bit hard to hear you. Your audio is not coming in very well, but I think what I got was, what is an example of multiple initial nodes?
Yes.
Okay. Multiple initial nodes in modern programming languages are rare or maybe non-existent, right? There is not usually a way to start execution of a program or start execution of a function in different places. So typically when we're making graphs of current, modern programming language, they will typically have a single entry, which is the call point. They may well have multiple exits, right? Multiple final nodes, because you can sprinkle return statements around in your, in your function or your method anywhere you want. However, we could look to things like, if we were writing an assembly language, we could have any number of points that we could jump into the code. And so there might be multiple legitimate starting points in the code. Finite automata, Kyle's pointing out, and I would agree, right? There are multiple initial states that something that a finite state machine could potentially have. But when we're deriving graphs from software, typically we're going to see single entry nodes.
So when we have those multiple entry nodes, where should we start though? Because we can cite either one of them.
If you had a graph with multiple entry nodes, and you were looking to come up with a set of test paths, I'm kind of going ahead of myself a little bit here. But if you wanted to set up a bunch of tests, let's say you wanted to set up a test that said, well, I want a set of tests that executes each of these nodes, right? Passes through each of these nodes. Well, I would have to have at least 3 tests, because I would have to have a test that starts here, and I would have to have a test that starts here at 2, and I'd have to have a test that starts here at 3. Maybe I would need more. I'd have to consider this graph a little more carefully to think about, can I get everywhere I need to get in only 3, or do I need more? But certainly you would have to have at least 3 test cases to start at each of the initial nodes. So let's talk a little bit about paths. And what is a path in a graph? A path is a sequence of nodes. and a sequence of nodes that are connected together by edges. The length of that path is the number of edges. This is an important distinction. It's very easy to get mixed up and say, well, if I had path, let's say 148, the first path that's listed here, what's the length of that? And it's easy to think, oh, there are 3 nodes there, its length is 3, and that is incorrect. There are 2 edges there, so this path's length is 2. And we can have subpaths. A subpath, this is a very simple concept. A subpath is just a piece of some bigger path. So if I had path 148, a subpath of that could be 14 or 48 or just 1 or 4 or 8. Those are all subpaths of that path. Now we get kind of back to what I was starting to talk about a minute ago about when we were talking about multiple entry paths, and that is a test path. A test path is a special kind of path through a graph. A test path is one that starts at an initial node and ends at a final node. And a test path represents the execution of some test case, right? Because you cannot, assuming we have, well, let's assume that this graph is derived from a piece of software, right? I can only begin the execution of that software at an initial node. And I can only stop the execution of that software at a final node or a terminal node. So a test path must start at an initial node, must end at a final node. We can have test paths that are executed by many different tests, right? So I have lots of different test data, but they may end up executing the same test path. I may also have test paths that can't be executed by any test. We'll talk a little bit more about that coming up. A very common example of graphs is the single entry, single exit graph. All test paths start at one node, in this case node 1, and they all have exactly the same finish node, final node, in this case node 7. So the set of initial nodes and the set of final nodes have exactly one node. So if we look at this graph, and this is a pretty classic double diamond graph, and this really is the representation of having an if-then statement here in node 1 and an if-then statement here in node 4, right? So we have a true and a false and a true and a false from the second decision. So we have 4 test paths through here. We could go 1, 2, 4, 5, 7, 1, 2, 4, 6, 7, 1, 3, 4, 5, 7, 1, 3, 4, 6, 7. So those are the different test paths that we can have through this path, through this graph, excuse me. A few more definitions. A test path visits some node if that node is in the path. Okay, this is a fairly straightforward definition. That means that test path 1, 2, 4, 5, 7 visits exactly those nodes. It visits node 1 and 2 and 4 and 5 and 7. A tour is when a test path tours some subpath if that subpath is a subpath of the test path. Again, pretty straightforward definition. So if we have some test path 1, 2, 4, 5, 7, it visits each of those nodes. It visits each of these edges, which is just the pairs of nodes put together in sequence, and it tours all of these possible subpaths. 1, 2, 2, 4, 4, 5, right? These are subpaths of length 1, and then it have a set of subpaths of length 2, then a set of subpaths of length 3, and finally the full subpath, or the full path, is also a subpath of length 4. So we have 2 more, I'm not sure definitions, but representations here. Path of T with a small t is the test path that's executed by test T, where path with a large T is the set of test paths that are executed by the set of tests represented by large T. The thing to keep in mind here is that each individual test executes exactly one test path, right? Each test is the complete execution, starting at some initial node, going through the graph in some way, and ending at some final node. So let's talk a little bit about reach. A location, which can be a node or an edge in a graph, can be reached from some other location if there's a sequence of edges that will take you from the first location to the second. And then we can subset reach into two different subcategories. We have syntactic reach. Syntactic reach is based only on the graph structure. So knowing nothing about the logic behind the graph, simply looking at the structure of the graph, is there a subpath to get from the first location to the second one? Then we have the more complicated notion of semantic reach. Semantic reach is satisfied if there's a test that can actually get from the first place to the second. And to do that, you have to consider the actual implementation logic. And if you go back for a moment to this double diagram, let's imagine for a moment that this first test here in node 1 is if A is greater than B. And then we have in node 4 another test if A is greater than B. Well, if A and B aren't changed by this action, then if the test in node 1 is false, then the test in node 4 has to be false too. A can't be greater than B in one case and not be greater than B in the other case, assuming again that we haven't changed either value. So that would make a path like 1, 2, 4, 6, 7, or 1, 3, 4, 5, 7. Those paths would be syntactically reachable, but not semantically, because the logic that's built in behind the graph would prevent that from ever happening. Okay, so what do we use graphs for? Essentially, we're going to take our software and we're going to make a model of the software as a graph. Again, usually a control flow graph. Then we're going to apply some criterion that requires tests that will require us to visit nodes or edges, or tour nodes or edges, or tour paths or subpaths, or some feature of the graph, right? We're going to have some criterion that says, okay, given that graph, you have to do this with the graph elements. So the test requirements describe the properties of the test paths. And then we can satisfy the test criterion if we have a set of tests such that for every test requirement, every individual test requirement in the set of test requirements, there's a test path in the set of paths that meets that test requirement. This is another one of those things where I feel like the definition is more complex than the idea, right? If we have a criterion that says execute every node, then that's satisfied if the set of test paths collectively contains every node, right? So it's not a tough concept. All right, let me check the chat here because there's a few things that have been going on. I'd argue if there's a syntactic path but no semantic path, it means the underlying code can probably be refactored. I'd have to think harder than that. I think that's probably true in a lot of cases. Is it always true? I'm not sure. But that's a very interesting comment. Are the nodes the same as an AVL tree? I'm not familiar with an AVL tree. We want to elaborate on that a little bit? Binary search tree. No, I don't think so. In a binary search tree, you generally have the concept of a single root, which is not necessarily an entry point, but there's some analogies there. But I think what a binary search tree does not have is the concept of an exit node. unless you're thinking that, well, it's an exit node when I find the thing that I'm looking for. But you don't really pass through, you don't traverse a path in a binary tree in the same sense. Doing a search on a binary tree, your edges are not unidirectional, right? You can go down an edge, but then you'll come back if you need to go down the other side of the binary tree. So it's not really the same kind of graph. All right, so we can have a couple of different types. We talked about syntactic reach and semantic reach. We can now use a couple of different types of criteria to try to do work on those. So first we can start with looking at structural coverage criteria. When we're looking at structural coverage, we're defining that on a graph only in terms of the structure of the graph, of the nodes and edges. So we're talking about syntactic reach. And so the goal of structural coverage is really to ensure that the control flow executes successfully all around through the graph. So what are some things we can do with that? Well, the first and simplest structural control criterion requires that each node in a graph be executed, right? Node coverage. Essentially, the test requirements, the set of test requirements contains each reachable node in the graph. So if we've derived our graph from the source code, and we have a control flow graph that we've derived from the source code, is node coverage the concept that we need to execute each node in the graph? Is that the same as what we normally consider statement coverage?
I would probably argue so, since every possible combination of every reachable node, I would say they're equivalent.
Okay. And are they measured the same? So are they equivalent? So they are functionally equivalent, because when we're making a control flow graph out of software, all of the statements, all statements, the maximum set of statements that don't have any kind of decision in them, get put into one node. Right? So if I just have a bunch of inline statements that I can't branch out of in any way, those all get compacted into one node. So if I've executed all the nodes, then kind of by definition of the control flow graph, I've executed all the statements, because all the statements have to be in nodes. But would I measure coverage the same way? If I have 50% statement coverage, do I have 50% node coverage?
Not explicitly, because there's going to be different sizes and lines.
Yeah, different sizes, right? So a great example would be if I had, 998 lines of code that just were all straight through, and then I had a little branch that had one line of code on each branch, and then back together again, and I run one branch. I have, what, 3 out of 4 or 2 out of 3, depending on how you want to draw it, node coverage, but I have
Wouldn't it also
999 out of 1,000.
Would it also matter on the domain knowledge? Meaning, like, if you value certain lines more than you do with others, that would give you more value out of the.
So that's possibly true. That's very hard to measure with any kind of criterion, and certainly not by a structural criterion like this, right? Which is just basically saying, hey, based on the graph, here's this piece of graph, here's this node or this edge that we have to execute. There really isn't a notion in this approach about weighting those in any way and saying, well, this one is a really important node, or this is a really important edge. That's an interesting concept that we actually aren't going to touch on here. But that's an interesting thought, because definitely not every line of software is equally important, or maybe you could argue that it is. That could be a good discussion on its own. So node coverage, yeah, it's functionally the same as statement coverage, but it can be measured differently because node coverage takes all the redundancy out, right? If there's 1,000 lines of code all in a row, from a node perspective, that's just one, right? So that will cause you to maybe have a little more realistic measurement of what your coverage really is. So next up, and slightly stronger than node coverage, we can have probably the next obvious thing to do, edge coverage. And in edge coverage, our test requirements contain each reachable path length up to 1. Now this is a little bit of a strange terminology. What is this about length up to 1? Well, that allows us to take on a special case. We have a special case perhaps. What if we have a graph that has only one node? It's the initial node, it's the terminal node. This is not that unusual, especially in simple methods where there's no branching, there's no decisions. This method just does some calculation. Well, we have to, by definition, we want edge coverage to subsume node coverage, right? So that anything that satisfies edge coverage, by definition, satisfies node coverage. So we have to add this slightly little odd terminology in here saying each reachable path of length up to 1, meaning including paths of length 0. So does edge coverage differ from node coverage? And well, sure it does a little bit. Because here in this example where I have an if statement without a then, I can achieve node coverage here with one test path. If I go 1, 2, 3, I've achieved a node coverage. I've covered all the nodes, but I haven't covered all the edges. To achieve edge coverage or to satisfy edge coverage, I'd have to have another test path through here that went 1, 3 and captured this edge right here. There are a few other programming structures that will also make node coverage differ from edge coverage. This is the simplest one and the most common example. So is edge coverage the same as branch coverage? So I think I see a yes. I wasn't watching when that yes popped up. Sorry, was there a comment? Okay, well, it turns out, yes, these are exactly the same and they're measured exactly the same. If we've covered all the edges, then we have by definition covered all the branches and vice versa, because a branch in code is an edge in that code's control flow diagram. So, okay, yep, this is what I already talked about, a path with one node and no edges. It may seem trivial that, oh, this is kind of a silly case that we have to add this up to 1 terminology and make it a little more confusing just to handle this weird case. But again, formally, edge coverage has to subsume node coverage, and that's why we have that as part of the definition. So if covering one edge is good, covering more edges must be better, right? Maybe. There are a number of ways to cover more than one edge, and one way is edge pair coverage. Edge pair coverage is exactly what it sounds like. It requires pairs of edges or all subpaths of length 2, or rather, for the same reason as we just talked about, all subpaths of length up to 2. Because length up to 2 allows for graphs with one node or with 2 nodes. So what does edge pair coverage look like in this simple graph? And yes, there are 2 initial nodes, which is a little weird, but it makes a good example here. I would need to cover 1, 3, and 3, 4. And I would need to cover 1, 3, and 3, 5. 2, 3, and 3, 4. 2, 3, and 3, 5. Now, normally with node coverage, or excuse me, with edge pair coverage, what we'll do is we'll just put 3 nodes together. I don't need to say edge 2, 3 and edge 3, 4, I can kind of shortcut that representation by saying edges 1, 3, 4. So this suggests an obvious extension. If one edge was good and two edges were better, why don't we just cover all the edges and we'll cover all the paths in the graph? The reason that we don't generally cover all paths in the graph is because any graph with a loop has an infinite number of paths. Infinite numbers are usually difficult, especially when we're trying to satisfy them with tests that we're writing. So let's look at this graph. We've got our entry node here at 1, we've got our terminal node at 5, we've got a branch at 1. We kind of come into 4 and then come back to 3 again, so that's some kind of loop. What is our node coverage? Our test requirements for node coverage is just cover the nodes, node 1, 2, 3, 4, and 5. What's a test path? Well, a possible test path, and there are always, there are often more than one possible test path to cover something, but a test path to cover this node coverage would be 1, 2, 3, 4, 3, 5. All of the nodes are executed. Now, if we look at edge coverage, we need to satisfy each of these edges. Can we do that in one test? Well, not quite, because if we take the first test, the obvious one, 1, 2, 3, 4, 3, 5, well, we missed this edge 1, 3. So we'll take that first test that covers many of the edges, but now we need another test path to cover this one edge that we missed. And that other test path could be the simple case of 1, 3, 5, and that gets us the 1, 3 edge. Now, if we look at edge pair coverage, I'm not going to go through each of one of these because this gets increasingly painful as we go, but we need 1 to 2 and 2 to 3. We need 1 to 3 and 3 to 4, etc. So we have all of these edge pairs. What tests do we need? Well, now we start needing considerably or significantly more tests. We can still start with the original one, and the original one covers 1, 2, 3 and 2, 3, 4 and 3, 4, 3 and 4, 3, 5, but it misses edge pairs like 3, 4, 3, for example. So we need at least one more test to catch that one. And then it turns out we end up needing 4 tests altogether to capture all of these. As we start going through some bigger cases, one way that I really like to do this is by just highlighting, and so I'll write all the test requirements, and then I'll write a test path, and I'll go through and I'll highlight this test path in, let's say, yellow. And then I'll go through and say, okay, 1, 2, 3, highlight 1, 2, 3 in yellow, and 2, 3, 4, highlight that in yellow. And then I can very easily see what's left that I need to cover. Okay, let's make another test path and cover that, and just continue highlighting in different colors as we go. You'll see some examples of that coming up, or possibly next week, I'm not sure. What if we want to accomplish complete test coverage or complete path coverage? Well, we need 1, 3, 5. 1, 2, 3, 5 is another path. 1, 2, 3, 4, 3, 5. 1, 2, 3, 4, 3, 4, 3, 5. 1, 2, 3, 4, 3, 4, 3, 4, 3, 4, 3, 4, 3, right, etc. So we have an infinite number of paths because we can keep going around that 3, 4 loop as much as we want to. And because this is structural coverage, right, based on the structure of the graph, there's no stopping criteria here. Right, there's no case, there's no data, no information about the program execution that would give us any reason to stop. According to the structure of the graph, I would have an infinite number of test cases. Okay, question in the chat. Does 1, 2, 3, 5 cover edge pair 2, 3, 5, but do we need to include the start code? I think we're got to go back here to talk about edge pair coverage. So 1, 2, 3, 5. So that does cover the test the edge pair 2, 3, 5, which is a test requirement? Do we need to include the start node? The start node, that full path 1, 2, 3, 5 is not one of the test requirements. The test requirements are edge pairs, right? So I have a test requirement for 1, 2, 3, and I have a test requirement for 2, 3, 5. I don't have a test requirement for 1, 2, 3, 5 because that's bigger than an edge pair. However, my test paths, the tests that I can write to execute, to go work my way through the graph to satisfy the test requirements, they all must start with an initial node and end on a final node. So how do we handle loops and graphs? Because obviously, as we said, if a loop contains a graph, then it has an infinite number of paths, and complete path coverage is infeasible. So for starter, there's a weak solution to this problem called specified path coverage, where basically the person doing the testing just decides, well, okay, how many times should I go around that? This is obviously a weak criterion because it depends on what the tester decides to do. The tester might make a good decision, they might make a bad decision. There is no way to justify logically by a criterion or a criterion. Yep. There's no way to justify your choice. So it's a fairly weak solution. Are there better solutions? I'm glad you asked. So dealing with loops and testing has been a topic for obviously a long time. You know, in the 1980s, a common approach was execute all the loops one time. It's, you know, not a bad way to start, but that leaves out some interesting test cases. Like, what if I don't execute the loop at all? What if I execute the loop more than one time? So that led to some rules in the 1990s for testing where, okay, let's execute the loop exactly 0 times and exactly 1 time and then more than 1 time. That's not bad, but that got refined a bit in the 2000s using the terminology of, or the idea of prime paths. So what's a prime path? So before we talk about a prime path, we have to define the term simple path. And a simple path from one node to another node, from node I to node J, that path is simple if no node appears more than once in the path, except that the first and last nodes might be the same. In other words, a simple path has no loops in it, but the simple path in its entirety could be a loop, but it doesn't contain any loops within it. So what is a prime path? A prime path is a simple path that does not appear as a proper subpath of any other simple path. And what does that really mean? Well, it really means a prime path is a simple path that can't be made any longer while still remaining a simple path, right? I've added on nodes at the beginning or at the end as much as I can. And if I add any more, it is no longer a simple path because a node will appear more than once. So let's look at this graph. What are some simple paths? Well, here's the list of simple paths in this graph, and they are all of the paths in the graph that do not contain a loop. So obviously, any of these paths of length 1 do not contain a loop. These paths of length 2, in this case, 1, 2, 4, 1, 3, 4, 2, 4, 1, they don't contain a loop, right? None of them contain the same node. Now we get to paths of length 3. When I have a path of length 3, now I'm starting to have simple paths that are themselves a loop. So 1, 2, 4, 1. Okay, that path does not contain a loop, but the path as a whole, the first node and the last node, are the same. And in this graph, I cannot have any longer simple path, because if I, for example, had a path 1, 2, 4, 1, 3, That's a perfectly legitimate path through the graph, but it's not a simple path because it contains a loop within it. So what is a prime path? A prime path is any simple path that can't be made longer while remaining a simple path. So 1, 2 is not a prime path because 1, 2 is a subpath of 1, 2, 4. And 1, 2, 4 is not a prime path because 1, 2, 4 is a subpath of 1, 2, 4, 1. So a prime path, again, a simple path that can't be extended any further. So that leads us to prime path coverage. Prime path coverage is, well, what we like about prime path coverage is that it's finite, right? It requires loops to be executed and it requires loops to be skipped. So for prime path coverage, the set of test requirements contains each prime path in the graph. And prime path coverage guarantees that we will tour all paths of lengths up to the prime path length, and it subsumes node and edge coverage. So this is very powerful, a very powerful graph criterion that is also, I'm going to say easily executed. I don't necessarily mean that it's simple, but it's not infinite, right? It has a very limited number of cases. An interesting point here is that prime path coverage does not subsume edge pair coverage. It does subsume edge coverage. It does subsume node coverage, but it doesn't subsume edge pair coverage. Why not? Because edge pair coverage would contain things like 2, 2, 2, right? From 2 to 2 and then to 2 again, or 2, 2, 3. Those are requirements for edge pair, but 2, 2, 3 is not a prime path because node 2 appears twice and is not the starting and ending node. So for prime path coverage in this graph, we have the prime path 1, 2, 3 and the prime path 2, 2. Both of those are simple paths. Neither of them can be made any longer. And what that amounts to is one test that requires us to not execute the loop and one test that requires us to execute the loop at least once. Now, these are not test paths necessarily, right? These are the prime paths. I would need to write test paths to execute them. Now, it turns out that this first one is also a test path because it starts at an initial node and ends at a final node. But this prime path 2, 2, this is not a test path. I'm going to have to make a test path that contains it, like 1, 2, 2, 3, for example. 1, 2, 2, 3 would be a test path, something I can execute that contains or tours that prime path. All right, going back to our earlier diagram. We talked about our simple paths. What are our prime paths? And I'll just look at a couple of these, like 1, 3, 4 is a prime path. I can't make it any longer because there's nothing before 1, so I can't extend it this direction. And if I extend it any further from 4, I'm back to 3, which means 3 appears twice without being the first and last node. So 1, 3, 4, for example, is a prime path. And so these prime paths, like I just described in the last example, one of these prime paths, 1, 3, 5, will require me to loop 0 times, right, to skip the loop. 1, 3, 4 will require me to loop at least once. And 4, 3, 4, another prime path in here, will cause me to execute the loop more than once. So a couple more definitions. Let's talk about touring. A test path tours a subpath if that subpath is a subpath of the path, which again, I find to be kind of a circular definition. But let's see, what will prime path do? If we tour the prime path 1, 2, 3, 5, 6, we can tour that path without side trips and without detours, right? We can tour that path directly just by executing that prime path. But we can also tour paths with side trips. A path tours, a test path tours a subpath with side trips if and only if every edge in the path, in the prime path, every edge in the test path is the same as every edge in the prime path in the same order. Okay, what does that mean? It means that we can go off of the path as long as we come back onto it again. So this tours 1, 2, 3, 5, 6 with a side trip to node 4, out to node 4, and then back to node 3 again, so that these edges, edge 1, 2, edge 2, 3, edge 3, 5, edge 5, 6, are all toured in the proper order. We can also tour a path with detours. And with detours, what we need to do is to tour all of the nodes in the right order. So touring this path, touring 1, 2, 3, 5, 6 with detours might be coming 1, 2, 3, 4, and then to 5, and then 6. We've still executed all the nodes in the right order, but we've no longer executed all the paths in the right order. So touring directly is the strongest way. Touring with a detour, touring with a side trip is slightly weaker. Touring with a detour is a little bit weaker than that. Why do we care about those things? Question in the chat. These aren't as strong as prime path coverage. Well, they're forms of prime path coverage, right? We would be talking about doing prime path. If the prime path 1, 2, 3, 5, 6 is what I want to tour, what I want to satisfy, doing it with a side trip is a way of satisfying it, a slightly weaker way of satisfying it, but a way of satisfying it. Why do we need these alternate ways of satisfying it? Often because we can have infeasible test requirements. An infeasible test requirement is a test requirement that can't be satisfied. There's no test I can write to satisfy this. When we're looking at a graph, structurally, I can come up with any test path I want, right? As long as there are arrows there, I can come up with any test path that I want that follows the structure of the graph. But when I'm actually getting to the point of writing tests in software, I have to start taking into account the logic that underlies the graph. And the logic in the graph might prevent me from executing the paths that I want to execute. So for example, the logic in the graph might prevent me from executing a prime path directly. Perhaps because there's an unreachable statement, there's dead code. We could argue, well, if there's dead code, it should be taken out. Normally I would agree, but there are also reasons not to take dead code out. It's there for future enhancement. It's there for readability. It's there because it's always been there and we don't want to have to recertify this piece of software. We may also have a subpath that can only be executed with a contradiction. I talked about this a little bit earlier. Is there a case where this particular subpath can only be executed if x is greater than 0 and x is less than 0 because of different decisions along the way? Obviously, both of those things can't be true. So I could have an infeasible path. And most test criteria end up having infeasible requirements. Interestingly, it's usually undecidable, right? Formally undecidable whether all test requirements are feasible. So we can't really predict ahead of time whether they're all feasible. If we don't allow side trips, if we insist on all of these prime paths must be directly toured, which is what we like to say because that's the strongest criterion. But if we insist on that, we may find that we have more infeasible requirements. And which is better? Is it better to just drop that, to eliminate that prime path because it's not feasible? Or is it better to tour that prime path with a side trip or a detour? And I would argue it's probably better testing to tour that prime path with a side trip or a detour than to not tour it at all, because the direct tour is infeasible. So allowing the side trips weakens the test criteria, but it's arguably better than not testing any particular prime path at all. So that leads us to best effort touring, right? And this is really just supposed to be a compromise that is something that's practical to accomplish. So we would want to tour or satisfy as many of the test requirements as we can, be they edge pairs or prime paths or whatever. We'd like to do them directly without side trips or detours, but when we can't, we'll accept a side trip or a detour to try to satisfy that test requirement as best we can. So now let's look a little bit at applying graph coverage, and we're going to start to look at applying it to source code. We're going to take a much deeper dive into the source code side next week, but we're going to start to look at it a little bit here. So for example, here I've got this little piece of function here. If x is less than y, then set y to 0 and increment x, else set x to y. Why are we doing this? I don't know. It doesn't matter. It's just a little piece of example code, but what would that look like on a graph, or how would that translate to a graph? And it would translate to this graph, where we have a first node. The first node is a dummy decision node. There is no executable code happening in this node, but we need this node because we need the edges coming out of it. We need an edge for x is less than y, and we need an edge for the opposite case, if that's not true, where x is greater than or equal to y. Well, if x is less than y, then we set y to 0 and we set x to x plus 1. So those are annotated here on node 2. If x is not less than y, we have this code, x equals y, so we'll notate that here. And then we come back together, and maybe this is a final node, or maybe we just keep marching on through more code. It's not really specified in this example, but we get this diamond graph for this if then else. And so all we've done is we've annotated that graph with the decisions and with the functionality of the code. We'll talk, as I said, a lot more detail next week on source code. We can also apply graph coverage very easily to things that aren't source code. So this should look kind of familiar to you, right? The 737 MAX MCAS system, nice state diagram. Well, we can look at this and pretty much say, yeah, I could apply graph coverage here. I could apply node coverage and make sure that I have tests that run through this finite state machine and end up in every state. Or I could have edge coverage so that I make sure that I go through every possible transition that's on this diagram. I could have edge pair coverage. I could figure out what the prime paths are, right? So all of the criteria that we just talked about for graph coverage on source code, I could equally apply to graph coverage on this finite state machine, as well as other things, but those are the two examples that I'm going to point to today. Short of that is graph coverage is really very, very flexible. If you can make a graph representation of something, then you can apply that whole set of criteria. Node coverage, edge pair coverage, prime path coverage. You can apply all of those to that graph that you derive from whatever you derived it from. All right, so now we're going to take a little bit of a turn here. And we're going to turn up the complexity just a little bit on graphs. And we're going to talk about data flow coverage. When we're looking at data flow coverage, we're going to take our graph and we're going to annotate our graph with references to variables. The goal of doing this is to make sure that values, variables in our graph are computed correctly and then are used correctly. So we have two additional things happening in our graph when we're looking at data flow coverage. We can have a set of definitions or defs. And a def or definition is a location in the graph where some variable's value is set. And then we can have a use. And a use in the graph is a location in the graph where some variable's value is accessed, is used, is referenced. So what might that look like? So here's a graph. We've got back to our double diamond graph. And we've annotated it a little bit with source code. And now we can say, okay, we have a set of definitions happening here. What is the set of definitions that's happening at node 1? Well, node 1 is defining or defing x. Here it is, x equals 42. Node 5 is defing z. Z is set to x times 2. Node 6 is also defing z. Where are uses happening in this graph? Well, at node 5, we're using x here on the R value. And in node 7, we're using x. We could also turn this notation around and say, where are we defing x? And we'd say, well, we're defing x at node 1. Where are we defing z? Well, we're defing z at nodes 5 and 6. So we can use whichever direction. We can say what's being defed at a node, or we can say where is a particular value being defed or used. That leads us to the concept of def use or DU pairs. And DU pair is a pair of locations in the graph such that the variable is defined at the first location and used at the second location. We go back one graph for a moment. So we have a DU pair here of 1 and 5. Because x is defined at 1 and used at 5. And we have a DU pair of 1 and 6, because x is defined at 1 and used at 6. Now we can start to look at a little more at DU paths. We can take those DU pairs and we can say, can I make a path out of that? So a DU path, a def use path, is what's called def clear if the path doesn't have another definition along the way, right? So if I def x and I go through this path and I use x without ever defing x again in between, then that path is def clear. If I def x and come through the path and def x again and then use it, that full path is no longer def clear because I did another def. The second half of it is def clear. Go ahead, Kyle.
The second definition of x is self-referential, like x equals x plus 1.
So that path would still not be def clear, but you'd have two def clear paths. You'd have a def clear path from x to x equals x plus 1, and then you'd have a def clear path from that definition of x to wherever it was next used. But if you define the variable, even if you define it using its in terms of itself, as long as you're not saying x equals x, which would be a dumb thing to do, then it really just counts as a brand new definition. All right, is the def use idea used in IDEs where it can detect what variables are declared but not used, or the other way around? Yeah, that's exactly what's happening. When your compiler tells you things like, there's a way to get to this variable, when your compiler or your IDE tells you there's a way to get to this statement without defining the variable, right? The variable might not be defined here. It's actually doing DU path analysis. Exactly right. So a DU path is a simple subpath that's def clear with respect to some variable, from the def of that variable to the use of the variable. So if we've got DU paths, how are we going to use them? Well, we could have a test path, and our test path DU tours at DU path You know, sorry, getting myself a little mixed up here on the definition. Our test path will tour some DU path if the DU path is a subpath of the test path and if it's def clear. And again, we can use side trips or detours if we need to. So that brings us to 3 fairly obvious criteria. We might decide to have a criteria to, well, let's make sure that we use every def somewhere, right? Anytime we def a variable, let's have a test that goes from that def to some use. Okay, seems reasonable. Or let's have a set of test requirements such that I have to get to every use of a def. Or even more strenuously, let's make sure we tour all of the possible DU paths. So more formally, that's all defs coverage, right? For every set of DU paths, the test requirement contains at least one path. Or all uses. For every set of DU paths to the uses, we have to contain a path, at least one path to each use. And all DU paths coverage, where we have to, our test requirements have to contain all of the DU paths from each def to each use. So each of these is a little more strenuous, potentially requires more test cases, but potentially is better at finding defects. All right, so let's look at an example. Here's our graph again, same graph as we were using a few minutes ago. What do I need to satisfy for all defs for X? Well, for all defs for X, I need to find a use for this def. So I could satisfy that with node 1 and then node 2 or 3, which is what my little bar means here. This just means, yeah, I could do 2 or I could do 3, it doesn't matter. So 1 and then 2 or 3 and then 4 and then either 5 or 6. Because I'm just trying to get from this def to some use. Now, what about getting from the def to all uses? Well, now I need 1 and 2 or 3 and 4 and 5. And also 1, then 2 or 3, then 4, then 6, because I have to get from this def to both of these uses. But it doesn't matter whether I use 2 or 3, because I only need one path to get there. But if we then go to all DU paths coverage, now I need to go 1, 2, 4, 5, and 1, 3, 4, 5, and 1, 2, 4, 6, and 1, 3, 4, 6. So I have more paths that I need to cover, and consequently, more test paths, and thus more test cases. Would the number of all uses increase if X was defined in 2 and 3? Yes, if X was defined in 2 and X was defined in 3, then I have to get from this def to all its uses. So I'd have to get from 2 to 5 and from 2 to 6. And I'd have to get from this def to all its uses. So I'd have to get from 3 to 5 and from 3 to 6. That's if X was defined in 2 and 3 instead of in 1. All right, we're near the end here. Let's take a quick look at the subsumption relationship between these criteria. So at the bottom we've got node coverage. Node coverage is not bad, but as you can see, it's not great because most other things satisfy node coverage. Edge coverage, for example, always satisfies node coverage. Edge pair coverage obviously always satisfies edge coverage. edge coverage, and thus edge pair coverage obviously satisfies node coverage. Complete path coverage, if we could do it, subsumes everything. Because obviously, if you've covered every path through the graph, there's nothing else you could do. The problem with complete path coverage is if you have a loop, you can't do it. Prime path coverage subsumes edge coverage, but not edge pair, as we talked about. It also subsumes all DU paths. All DU paths subsumes all uses subsumes all defs. And then there's a looser relationship between the def use approach and and the structural, the edge coverage and node coverage. So if we simply do all defs, we're actually not guaranteed to cover all edges and all nodes. These guys over here we didn't talk about. I merely hadn't deleted them off the slide from a previous iteration of the course where we talked about that too. But really, I think the ones we talked about are enough. All right, so this graph kind of gives you an idea of, this subsumption relationship gives you a rough approximation of how effective a criterion is going to be at finding problems, right? The further up we go up the subsumption relationship, the more faults are likely to be found. But the more work is probably going to be necessary to be done. All right, so summary here. Graphs are a really powerful abstraction that we can use for designing tests. Graphs come in a lot of places. We can get them out of source code. We can get them out of a lot of other places. And we can use these various criteria, much like last week when we were talking about all combinations versus pairwise versus prime path, right? We can use different combinations to give us different cost and benefit, right? We can go up that subsumption graph and get higher cost tests that are going to find more defects, probably going to find more defects. Or we can go down the graph and reduce our test cost at the risk of possibly not finding as many defects. So we have a lot of flexibility when we're using graphs for testing. All right, that takes us to the end of the graph lecture portion. Any questions here that we want to talk about before we take our break? All right, so we've got two tonight. Both of these are out of the textbook, making it really easy for you to go back and see more about it. You can see what groups are going to be talking about which sections. So here we go, number one. We've got a graph defined as follows. It's got 4 nodes, 1, 2, 3, 4. The initial nodes are node 1. The final nodes are node 4. It has these edges. So first, not too tough, draw the graph. And then I want you to list test paths. And remember, a test path has to start at an initial node and end at a final node. So list test paths that satisfy node coverage, but do not satisfy edge coverage. Or explain why that's not possible with this graph. And then list test paths that satisfy edge coverage, but do not satisfy edge pair coverage. Or explain why that's not possible with this graph. And then list test paths that satisfy edge pair coverage. All right, fairly clear. Any questions before we start? All right, I'll set this up for 20 minutes. All right, welcome back. Let's start off going to the Hufflepuffs. And Hufflepuffs, please show us your graph.
Cool. Can you guys see my screen?
I can.
Sweet. So we just used a tool. So this is what our graph would look like.
Okay, great. So I'll just point out, I've mentioned this a couple of times over the course of the semester, but I'll point it out again on the textbook website. There's a couple of useful tools, including this one, that will draw your graph and will tell you other things about like what your edge pair requirements are and everything. And these are perfectly good to use. So continue. I just wanted to make that interruption. Sorry.
Oh, cool. Yeah, so we did the exercise here. I don't know if you want to, our team is only responsible for just drawing the graph, but
Yeah, okay. So good graph. And I'll leave you guys off there. And then we're gonna go to let's see, the Slytherins. And so Slytherins, what test paths do you have that satisfy node coverage but don't satisfy edge coverage?
We didn't discuss who's going to share, so I guess I'll hop on and share.
Okay.
Let me share my screen. Looks like I'm having permission issues with that. If someone else could.
I can do that.
Or, okay, thank you.
Sure. So
All right, you
So,
got your graph. Mhm.
yeah, you can see my graph, right? So this is not possible. Like if we have to cover every node, it also covers the every edge.
Okay, so
So
you're
1, 2,
saying,
3. Yes.
okay, so you're saying there is no test path that satisfies node coverage but does not satisfy edge coverage?
Yes. Every node coverage path will also cover edge coverage.
Okay, does anybody disagree? Well, I'm glad no one disagrees because you're absolutely right. There's no other, basically there's no shortcut, right? There's no way, like for example, if you could go, if 3 went to 4 instead of to 2, then you could say, well, 1, 2, 3, 4 covers all the nodes, but it doesn't cover edge 2, 4. But in this graph, there's no way. Everything that covers everything that satisfies node coverage also satisfies edge coverage. All right, thank you. All right, so let's go to Gryffindors. And Gryffindors, what do you have for test paths that satisfy edge coverage but do not satisfy edge pair coverage?
I can go if no one can go, if no one wants to. We use the whiteboard, but I realized that after the breakdowns, it just disappeared, so we don't have anything to share now.
Okay, yeah. So you were annotating on the Zoom whiteboard.
Yeah. But I try to recall what we did.
Okay.
We have the test pass 1, 2. Well, let's see. Can you share your screen, Doctor? Like the test, the route.
Yes. Let me go ahead and share that, and I'll bring up the graph.
So
Okay,
we have 1, 2, 3, 2, 4 is the answer, because it doesn't cover the edge pairs 2, 3, 2.
Okay,
And
so
3, 2, 4. Well, 3. I'm sorry, 3, 2, 3 is not covered. Is the edge pair is not covered by the test path 1, 2, 3, 2, 4.
okay, good, very good, thank you. All right, let's go over to the Muggles. And do you have anything else or anything different? Let me stop sharing my screen.
Let me share my, here it is. So this one is the exact same with a graphing tool. And
Okay.
we are kind of not sure about whether we add 3 to like, because it's kind of a loop. So we add another more 3 to
Okay,
here.
so you're one ahead there. I've still got you on part 3, which is, do you have any test paths that satisfy edge coverage but don't satisfy edge pair coverage?
Yes, I think that is what we got. Yeah.
Okay, and so what edge pair or edge pairs does that not satisfy?
3 to 3 and 1 to 4.
Right, 3, 2, 3, and then 1, 2, 4. That's the other one, and the Gryffindor team, without their notes in front of them, they were a little bit hard pressed to a little hard to come up with their full answer that they had earlier. But yes, 1, 2, 4 is the other edge pair that isn't covered by that test path. Good, thank you. All right, and then last, let's jump over to the Ravenclaws. And Ravenclaws, can you give us a test path or test paths that does satisfy or do satisfy edge pair coverage?
Yeah, can't share screen. It's a pretty simple answer. I'll post in chat. So we have 2 tests. The first one will cover, I guess, branching off into node 3. So it'll cover 2, 3, 2 as well as 3, 2, 3. And then we have a second test that goes from 1, 2, and 4.
All right, so your first test path, 1, 2, 3, 2, 3, 2, 4. That covers all of the edge pairs except 1, 2, 4, and then you have another test path that covers that, and that does indeed give you complete edge pair coverage. Great, good job, thank you. All right, so from here we'll jump into exercise number 2. And so we have much the same thing here. We're going to take this graph, we're going to draw the graph, but now we want to consider test paths. So which of these are test paths on this graph and which are not? And if not, why not? And then again, we'll list the requirements for edge pair coverage. And then I want you to think about, given these test paths, or all of the ones that are valid, do they satisfy edge pair coverage? Why or why not? And then finally, if we have this prime path and we have a new test path, does that test path tour the prime path directly, or does it tour it with a side trip or detour? And if so, what's the side trip or detour? All right, so we're 6:35, so I'm going to make this a little shorter at 15 minutes. As soon as I find my window, there we go. All right, 15 minutes, and I'll see you back here in a bit. All right, seems like some good work going on in the groups. So let's see, we're gonna go over to the Muggles first. And so Muggles, show us your graph.
I could just, yeah.
All right. We've got 1 to 2, 2 to 1, 1 to 3, 3 to 1, 2 to 3. That looks like a great graph. Thank you.
You probably just need a starting arrow at 1, but other than that.
Ah, well, good point. I didn't notice that. But that is a good point. To be technically correct, it should have a little starting arrow at 1. All right, so Ravenclaws, let's go to you next. And of these paths, of these 5 paths that I've provided, which of them are test paths?
So I'll go ahead and just put in the chat.
Okay. Or you can just talk to it if you want. All right, so go ahead and explain what you've, go ahead and explain what you've got here.
So for P1, it's 1, 2, 3, 1. So it doesn't end at the final node.
Okay.
And P2, P3, we can say that they are the test path. And but P4 and P5, for P4, we don't have a start node.
Okay.
And for P5, 1, 2, 3, 2, 3, the edge 3, 2 is not part of the graph. So
Okay. Perfect. Great. Good job.
thank you, Professor.
All right. Let's go to. Who's next? Where'd my
I think Hufflepuff is next.
lost my correct window here. Yeah. Okay. Hufflepuff. Hufflepuffs, what's your edge pair coverage requirements?
We got 1, 2, 3, 1, 2, 1, 1, 3, 1, 2, 1, 3, 2, 1, 2,
2, 1, 2.
2, 3, 1, 3, 1, 3, and 3, 1, 2.
All right. Good job. That is correct. Thank you. All right. Next, we're going to zip over to the Slytherins. So given those valid test paths, do those test paths satisfy edge pair coverage?
So I'm gonna, can you see my screen?
Yes.
Okay. So we traced, all these were all the paths that we came up and we traced them and we found that we couldn't find the edge 2 to 1 and then 1 to 2. And then we also couldn't find 3 to 1 and then 1 to 3. So we said the test paths don't cover all the pairs.
Okay. So scroll down again for me just a little bit. Thank you. All right. So 2, 1, 2 and 3, 1, 3 are not covered. Okay. That is also correct. Good job. Thank you. And now we're going to go over to the Gryffindors. If we've got a prime path 3, 1, 3 and we've got a new test path 1, 3, 1, 2, 1, 3, does that path tour the prime path directly? And if not, does it tour it with a side trip?
Yeah, we used a different whiteboard site and then my Chrome has crashed. So does someone from the group have the link still? And can share.
I can try the link real quick, but I did also write down our answer. So if it does work out, I have it. Okay, so this doesn't have our whole thing, but I can share this 1 second.
Okay.
All right, so this was, the graph we're looking at. And so to answer the question, does P6 tour the prime path directly? We said no, it doesn't, because it has like a little side trip, which answers the next question. And so the side trip was that instead of going, to 3, 1, and then 3, 1 after another, it went to 3, 1, and then it did a side trip of going to 2 and then to 1 again before reaching 3. So in this case, you can consider the side trip either 1, 2 or 2, 1, because you only need to go to the node 1 once before you go to 3 again.
Great. Good job.
All right.
All right. So that covers us for this week. And I just saw your note, Kyle, that my audio hasn't been that good. Has that been a thing for everyone?
Yeah.
Oh, well, I'm sorry about that. You all sound fine to me. So next time, please feel free to let me know earlier, and I'll fiddle with my mic or reset my adapter or something like that and try to get that right. So my apologies. All right. Any questions before we break? The exercises with answers is posted. And I think that's it. I guess I'll remind you again that the current assignment is due next week. Currently due before start of class, but if I don't hear any objections to the grading change, then it will become due by midnight on Monday. Anything else we want to talk about?
For assignment 4, there's a discussion that asks like what's a reasonable amount of test cases.
Yes.
So can you like provide some insight into that?
My insight to that is, what do you think a reasonable number of test cases is, and why?
I mean, going based off the preconditions, like I think there was like a total of like 8 different preconditions. So if we did that and we just did a simple 2 blocks, so true false, I think let me see here. 1 second.
What was this for again?
This is for assignment 4.
Oh, I haven't looked at it yet. Oh my.
Yeah, so for like all combination coverage, it'd be like 128. And then for pairwise coverage, it'd be 18. So there's quite a bit of delta there.
There often is a very big difference between all combinations and pairwise. This is the power of pairwise. But what I'll encourage you to think about, and I talked about this in an entry I made on the chat, or the discussion board, whatever you want to call it. Think about the kinds of things that could go wrong, right? The kinds of faults that you could have in Cal. And you've got an example of 5 of them from your last assignment. I think the last assignment, right? Where you had to, where we were doing other kind of testing and there were 5 faults that were planted in there. So think about, am I likely to be able to find those 5 faults with, what did you say your pairwise was? 5 tests or 8 tests?
It would be 18.
18.
If we just went off the preconditions, yeah.
Okay, so am I likely to be able to find those 5 problems and more like them with 18 tests? Maybe. Am I likely to find them with 100 tests? If you had a different input domain model and your pairwise came out to 100 tests, I think I forget off the top of my head who posted. I think they said they had something like 120 tests or so for their pairwise after they refined their input domain model. Does that feel like a number of tests that would be likely to detect anything that could possibly be wrong in there? On the other hand, if you had 10,000 tests, does that seem reasonable? So there's a little bit of a gut feel involved here, and I understand that a good gut feel requires experience doing this, and you don't all necessarily have experience doing it. But if you think about the arbitrary kinds of defects that you might inject into Cal, think about, okay, does my body of tests, is it likely to find all those possible things? And if you're feeling like, yeah, I'm not really sure that I would catch one of them, for example, was given 31 days in the array instead of 30 days. And if you're feeling like, yeah, I'm not really guaranteed to catch a problem like that, then maybe you want to make some adjustments to your input domain model so that you're feeling more comfortable that you would be guaranteed to catch problems like that. On the other hand, I can freely tell you, if you're coming up with, I did my input domain model, I did pairwise test optimization on it, and I have 1,000 tests. I'm not sure what your input domain model looked like, but it's probably way too many choices, because that's sort of off the deep end of kind of a ridiculous number of tests for something of Cal's complexity. And like, if you had 5 tests, I think we could probably all agree on gut feel that 5 tests is really just not going to be enough to thoroughly test something of Cal's complexity. What is the right answer? Well, I have some ideas, but that's part of what I'm grading you on. So, I'm not gonna be specific with what my ideas are, but I'm just trying to give you some, what you should be thinking about when you're thinking about, hey, did I get a reasonable number of tests? A couple of them, Cal's more complicated than that. Thousands of them, Cal's not that complicated. So, what's a good number? There is no one good number, but you should feel comfortable that if I took Cal and I made those 5 changes from the last assignment, and then I made 50 more or less like them, you should feel comfortable that your set of pairwise tests would be likely to catch them. And if you're feeling not comfortable, like, oh, what if I change the number of days in January? What if I change the number of days in December? What if I change that and to an or? What if I change that divide to a mod? If you're not feeling comfortable that your test set would catch those things, then you probably want to revisit your domain model and refine it a little bit and rerun the pairwise analysis of it, or the pairwise optimization of it. So I hope that's helpful without, you know, telling you what the answer is that I want to see.
Yeah, thank you.
Okay. All right, well, I hope you all have a great night and a good week. And this week's quiz will be due on Friday. I will go double check that right now just to make sure that it's due on Friday instead of Thursday. And then I'll see you next Monday. Take care, everyone.
Have a good night,
Thank you,
Professor.
Professor.